It has two parts. The purpose of the first part is to use the universal law of gravitation to find the mass of a black hole, and the purpose of the second part is to see if we can get specific trajectories out of the spaceship using only gravity from other objects in space. And we have two models. For the part 1, we have a model that lets us calculate the average mass of a black hole. For part 2, we have a model that lets us set certain velocities to a spaceship to let it be affected by the gravitational force of a planet and its moon. And the fundamental physics principles are the same for both parts. We have Newton's second law, which states that net force is equal to dp over dt, and from there we can get the momentum update formula, the position update formula, and the velocity update formula. We can also get F-net parallel and F-net perpendicular from Newton's second law, and F-net parallel is responsible for determining the speed of an object, while F-net perpendicular determines its direction. We also have the universal constant g, which is shown, and from here we also have the universal law of gravitation, which is equal to negative g times mass 1 times mass 2 over r squared times r hat. A brief preview for both parts is that for part 1, we found the mass of the black hole to be 1.45 times e to the 34 kilograms, and for part 2, we got a trajectory that was influenced by both the planet and the moon, but it was not a figure 8. For part 1, the system is the star, and the surrounding is the black hole. The initial conditions are shown in the code, where delta t is 86,400 seconds, and the mass of the star is 2 times e to the 30. And here we have the code for part 1, starting with finding the initial and final velocities and momentum, and then we found delta v and delta p from there. From there we found dp dt, which is equal to the net force, and then we split the net force into parallel and perpendicular components. And then in order to find the mass of the black hole, we rearranged the universal law of gravitation to isolate the mass of the black hole on one side, and then from there we also printed out the arrows for the net force, its parallel component, and its perpendicular component. There are no similarities or differences or possible sources of error for part 1 because it was all a computer model, and we found that the average mass was equal to 1.45 times e to the 34 kilograms. To answer the what if for part 1, the net force and its parallel and perpendicular components are the same as the rate of change of momentum in its parallel and perpendicular components, as we can see in the momentum principle or Newton's second law. For part 2, our system is the spacecraft, and the surroundings include the planet and its moon. And we can see the initial conditions in the code on this slide. And here we have more of the initial conditions, where we have the initial x velocity to be 3.4 times e to the 3, and then we have the y component being equal to 4.5 e to the 4, and it's in scientific notation. And from here we used the universal law of gravitation to find the net force acting on the moon by the planet and the ship, and similarly we used the universal law of gravitation to find the net force acting on the ship due to the planet and the moon. And we also used Newton's second law to get the velocity and position updates for both the moon and the spaceship. And like part 1, there are no similarities or differences because we only have a computer model, but for possible sources of error for not getting a figure 8 orbit may be because we chose initial x and y velocities that did not give this orbit, but we did get a shape that has ovals in ovals, and here's a picture of that shape. To answer the what if for part 2, there actually was no black hole, So we can start by including that in our model, and we can just include that to keep this system, or the system and the surroundings, simple. And there may be no dominant interactions, because even though the black hole has the largest mass, we're probably going to make it the furthest away from the system. So even though the moon and the planet are very close to the spaceship, they have significantly less mass, so everything in the end balances out. Thank you for watching.